Groups and group theory. This is an introduction to group theory. We won't be going particularly deep into it, but just to show you what groups are and go through a number of key examples of different types of groups and look at some aspects of the mathematical study of them. Okay, so I'm very quickly going to recap the definition, 5.1, the defining conditions for a group. Then I'm going to reconnect with the example that we were working through last time, which was the group of symmetries of a triangle. And then we'll look at some more examples later on in today's session. Okay. So last time, it was last Wednesday down in Jeffrey Manton, we looked at the idea of a group. So a group is when, in mathematics, we have a set of elements, set of objects, and an operation called a binary operation on them. Okay. So the binary operation, examples of a binary operation are things like the arithmetic operations of addition and multiplication on numbers, or addition and multiplication on vectors, any kind of addition-like or multiplication-like operations on mathematical objects. Okay, you've got similar kind of operations on matrices, vectors, numbers, and functions as well. You can have functions as basic objects and be adding them together, multiplying them together to create new functions. Those are all examples of binary operations, where you have some kind of domain of elements, some set of elements, and an operation where you take a pair of elements from the domain, an ordered pair, first one and a second one, and combine them together in some way to produce another example of the same class of object. That's a binary operation. And now you can have a set and a binary operation, and that would encompass a huge amount of possibilities. A group is where that set and operation are well behaved in some basic ways, where they satisfy some basic kind of systematic structural properties, which are commonly found in interesting mathematical situations. And those properties are here, these numbered properties 1 to 4. Let's just very quickly go through these and then return to our example from last time. So the first property is closure. When you take two elements from whatever set or domain it is, operate them together using the operation, you again get an element that's in the same set. So the set that we refer to that type of property as being closed. The set is closed with respect to the operation. Okay? You never start in the set, get a pair of objects, operate them together, take the product together, and suddenly you're outside of the set. Okay? The set is like a closed system for the operation. Secondly, the operation, so for a group, the operation has to be associative. Okay? And associativity is extremely common. All those properties, all those basic examples of operations, addition-like and multiplication-like operations, whether they be numbers, functions, matrices, vectors, they are all associative. Okay? When you take the product of A times B times C in this order, it doesn't matter in which way you evaluate the products in pairs, you always get the same answer. Now, there are examples of operations which are not associative. If you take division or subtraction as an operation, work through some examples, you will soon find that it is not associative. But subtraction and division we don't consider to be kind of, real, that they aren't operations, We don't give them the same stature as addition and multiplication, for instance. So most of the key important operations we consider in mathematics are indeed associative. And properties 3 and 4 kind of go together. Property 3 says there's a very special element present in your situation. This element is called the identity. And when you operate on when you take the product with any other element with the identity, the other element is left unchanged. You just get back the same thing. So for example, if it's an addition-like operation, then 0 will be the identity element, because you add 0 to something, it doesn't change. If it's a multiplication-like operation, multiplication of numbers, the identity is going to be the number 1. Multiplication of matrices, the identity is the identity matrix. That's why it's called that. Okay. And so on. Okay, so any questions about the axioms? Anything you'd like me to clarify? So they're presented in a general abstract sense there. What's on the screen there isn't talking about any particular group. It's just laying down the pattern of properties that define what a group is. So any system which meets these properties is called a group. Okay? And the universe of groups is very, very large. There's a lot of structure there. There's a lot of properties that are shared by all groups, a lot of properties that are shared by important subfamilies of the universe of groups, and so on. Okay? So what we're going to do now is continue with this example, important example, so this page is the page of notes from last lecture. I'm going to complete some things on it. So this was the dihedral group D3. The dihedral group D3, we talked about this last time. This is the group of symmetries of a regular triangle drawn in the plane. So we think of, seeing the diagram there at the top left, we think of a triangle which is drawn centered at the origin. And we investigated this a little bit last time. We found it had 6 symmetries. 6 symmetries. 3 rotations and 3 reflections. It has reflectional symmetry in each of these axes, going through one of the vertices and the midpoint of the opposite side. You reflect the plane in that axis, it's the same triangle you're looking at. The individual points on the boundary have moved around, but it's still the same triangle as a set. It also has 3 different rotational symmetries. You can rotate it 1/3 of a turn, moves each vertex on to the next one in order, or you can rotate it 2/3 of a full turn. And those are, we're denoting those by r and r squared. Okay? So r goes 1/3 of a full turn anti-clockwise, r squared, now that squaring there refers to the operation of composition. Because these elements, these objects, are symmetries, they're transformations of the plane. The appropriate operation is to compose them, to run one operation after another. So we have r and r squared, and if you think about what r cubed would be, if you rotate the triangle 3 times, well, that's rotating it 1 full turn, which as a transformation of the plane is the same as doing nothing at all. That's the same as not rotating the plane at all, or rotating it by an angle of 0. This turns out to be the identity transformation. Transformation that sends every single point in the plane to itself. Just leaves everything in place. These are our 6 elements. Now the group is a lot more than just listing the 6 elements. If that were the case, then the group would just be the same kind of object as a set, just a collection of stuff. And there's not a whole lot you can say about just a collection of stuff, just as a pure set. Okay? But the group is the set of elements together with the operation. Okay? So this group consists of these 6 things together with the operation of composition. Okay? Composition of functions. Because if you apply one symmetry to the plane, the triangle is left unchanged. If you then apply a second one, so you're composing the 2 symmetries, the triangle is again left unchanged. So the composition of 2 symmetries is again a symmetry. Group is closed under this operation. And we can kind of expose or show everything that's going on in the group by constructing a multiplication table. So this is what we started last time, and we'll complete now. This is called a Cayley table after the mathematician Cayley, but what it is just a multiplication table for the group. So here are the elements of the group, indexing the columns and rows of the table, and inside in each entry in the table, see this explanatory diagram over here, in the row corresponding to the element gi, and in the column corresponding to the element gj. We put the product gi product with gj. We have to set a convention for how the ordering goes like that, because these operations are not necessarily commutative, and this operation, composition of functions, is non-commutative. So if you swap the order of the pair of elements, you could well get a different element. You don't necessarily always get a different answer, but you often do. So you have to fix an order. when we started working out products last time, this was as far as we got. Let me just work out one more, and I'll just show you how the rest of the table completes. I mean, I did set this for you as an exercise, ask you to think about doing this. So we've got the products of any rotation with another rotation. They all give you rotation. We started working out products of rotations with their reflections. So then, for instance, I'll just do one more detailed example and then select table. So this entry here, this next gap here where I'm pointing to. So this is the element r squared after S1. Okay, the thing that's going to fill that gap there is r squared composed with the reflection S1. Now this is going to be another element in the group. The question is what element? Now, when we think about it last time, see, if you apply a reflection to the plane, everything that's right-handed in the plane becomes left-handed. Okay? You think about an actual hand sitting in the plane, you reflect the plane, it switches to the left-handed hand, wherever. And then applying a rotation, well, rotation doesn't affect handedness. Rotation leaves handedness alone. So that means the composition has still flipped right-handed stuff into left-handed stuff, vice versa. So the composition will be at one of the reflections. It isn't just going to be a rotation. Now, we can figure out which one it is by tracking the effect on a sample triangle. Now we agreed. So the reflection axis for S1 is this reflection axis here. Check back in the notes. Now when you apply S1 to it, how does the triangle change? Well, the vertex A stays in the same location because it's on the reflection axis, and the vertices B and C swap positions. We then have to apply the second transformation, which is r squared. So we rotate it by 2/3 of a turn anti-clockwise. So A started out here, it's going to end up here. B started out here. Sorry, C started out here, it's going to end up here. B started out here, it's going to end up here. So from start to finish there, from left to right, we've got the composition. Starting with this triangle, ending with this. It is a symmetry of the triangle. It's the same triangle as a geometric figure sitting there. And by looking at it closely, we can identify which one it is. And you see that, the vertex B has stayed where it is, and the vertices A and C have swapped position. So this composite symmetry, composite transformation, is clearly reflection in this axis of reflection, that long dashed axis of reflection. And by the way we set up the notation, that was S2. This was the reflection axis of S2. So that explains why S2 goes in this. Okay? R2 after S1 is the reflection S2. So by examining the individual compositions like that, you can see what the rest of the table is. Okay? Now the rest of the table, once you've got all of that, you can more or less, well, there's some other kind of group ideas or properties of groups you can use to quickly fill it out. So we've already seen the reflections S1 and S2, so we have to see the reflection S3. We've already seen the reflections S2 and S3 in this column, so we have to see the reflection S1. Then you get, well, this one down here, S1 after R has to be different to R after S1, and it can't be S1, and the other one is S3, so I'm quickly, by a process of elimination, I'm quickly identifying which entry it has to be there, but using some other properties I'm not exposing, you can figure all of these out using this kind of step-by-step process as well. So it goes S1, S2, S3, and it will go S2, S3, S1, and S3, S1, S2. Then we come to thinking about, so those are all the compositions, a certain reflection after rotation. And then we come to the next, so the lower bottom right grid of the table, where we have to work out the composition of two reflections. What do you get when you compose S1 with itself? Compose S1 with S1. This axis here was the axis for S1, going from vertex A there to that diagram. When you apply reflection in the axis S1 twice, what do you get? As a transformation of the plane, which transformation is that? If I take my hand, my right hand, if I reflect it, it becomes my left, it becomes a left hand. If I could reflect it. But if I reflect it again, back to the same hand. If you take a mirror image of a mirror image, you're looking at the original image. So when you compose any reflection with itself, that's the same as doing nothing at all. So that's the identity. Okay? S1 composed with S1 is the identity. For the very same reason, S2 composed with S2 is the identity. S3 composed with S3. Now, what about composing two different reflections? So this gap up here, in this element here, you need to put S1 after S2. Now, it has to be an element of the group D3. Which of the 6 elements, which type of element is it going to be? You reflect the plane twice, okay, in two different axes, so it's not going to be the identity transformation. But when you reflect once, you know, the handedness of things, chirality is the technical term we use for handedness. The chirality of stuff flips, changes when you reflect once, but when you reflect again, it flips back to the original configuration. So reflecting twice, or composing two different reflections, it can't be a reflection. Because things switch handedness under one reflection, but they switch again under the other one. So everything's back to the same handedness it had. So that means the only other option then is that it has to be a rotation. So we know by a process of elimination like that, that S1 composed with S2 has to be either R or R squared. It's not going to be the identity. Now to work out which particular one it is, you can label the vertices of your triangle and just work it out. So this axis here was S1. The axis S2 was the vertical one. So what do we get when we apply this rotation? Well, we have this first triangle. We're applying S2 here first. So S2 gives it the configuration BAC, like this. Fixes B and swaps B and C. Sorry, fixes B and swaps A and C. And then you have to apply S1. The S1, okay, S1 is still this axis from the bottom right to the top left. Still the axis going through this lower right vertex. So when you apply S1 to this triangle here, C is left fixed, and the other two vertices swap. So we have B down here and A down. The composition transformation is just this one-step transformation from the beginning to the end. Has to be a rotation. Can you look at it and figure out which rotation it is? Yeah, because ABC has now moved to ABC. So everything has gone on 1/3 of a turn anti-clockwise. So clearly, this is the transformation R, the basic 1/3 of a full rotation. So S1 composed with S2 is the rotation R. So this is an R here. Any guesses of what goes here to the right of R on the table? R squared. Has to be R squared, really. You can prove, as a consequence of the axioms, you can prove, it's not too hard, you can do, I'll leave it as an exercise. In the body of a Cayley table, or a finite group, in the body of a Cayley table, in any row or column, every element appears once and only once. Okay? So if you look at any column or any column or any row of the table, in the interior of the table, so forgetting the row and column headings, each group element appears once and only once. So the one missing from this final column here is R. One missing from this row here is R squared. one missing from this column here is R, and finally the one missing from this row across here is S. So that's how the table completes. So this now is the complete multiplication, the complete composition table, operation table for the group D3. We've identified the 6 symmetries of the triangle and also how those 6 symmetries intercombine, how they compose with each other to give other symmetries. So in principle, everything about the group can be drawn just from that table, can be derived from the table. The Cayley table is a complete description of the group as an abstract algebraic object. Okay. Any questions? Any clarification you'd like me to give you? Now, there's nothing earth-shatteringly interesting in some ways about a triangle. It's a pretty basic kind of object. But what we're studying here is, the possibilities for symmetries of objects. You could very much do this analysis for the symmetries of any kind of regular two-dimensional polygon. Square, pentagon, hexagon, septagon, and so on. There's no reason to confine yourself to 2 dimensions. We can also talk about symmetry groups of 3-dimensional objects. Any dimensional object. Okay. So this is an initial example of the large family symmetry groups of geometric objects. Okay. So, as an exercise that kind of you're prepared, you can begin straight away without any further theory. Really, is investigate Cayley tables. Investigate the Cayley tables for in similar fashion symmetry groups of the regular square, pentagon, hexagon, and so on. Okay? 4-sided, 5-sided, 6-sided. Okay? You can investigate those in a similar way. This would be D4, D5, D6, and so on. The hexagon has 12 symmetries. It's got 6 rotational type symmetries, including the identity, and it's got 6 different axes of reflection. Okay then. We will go and look at some other examples of groups. But before that, we're going to return to the notes and do a little bit of abstract group theory. Just a very little bit. So you can kind of, let me show this to you. In one way, you can consider group theory as just the study of all the consequences of these axioms. Okay. If you have some kind of algebraic system which satisfies these 4 properties, what other consequences, what other facts do you know about it? Or what are the possible? What are the possible groups? How many different types of groups can you have? How many different groups can you have of a certain size? We just saw one group of size 6 here, of order 6 elements in it. How many other ones are there? How many different groups of order 6 are there? It's not an easy question to answer. It's not a trivial question to answer. So that's one example of a kind of overall structural question that group theory attempts to answer. There's obviously an upper bound. you can't have an infinite number of different groups of order 6 because there's only a finite, there's 36 spaces in that table. There's obviously only a finite number of ways of just sticking down 36 elements, of arranging the 6 elements into a 6 by 6 grid. And most of those will not be legitimate Cayley tables for groups because they'll break some of the axioms. But exactly how many groups of order 6? No, that's a hard question. Now, you're familiar with the term commutative for an operation. An operation is commutative if it doesn't matter in what order you have the arguments for the information. We also use the term abelian. So abelian, which is made from mathematician Abel's name, Norwegian mathematician, I think. So we call the group abelian if the operation is commutative on the group. Okay. It's also kind of interesting is that you can often see the term abelian used without the capital letter. It's one of the few terms that originally came from someone's name, so normally those would be capitalized, but it's so common and it's so often used, it's kind of lost the capital A. So I think most of the time you see the adjective abelian, it's with the lowercase a. Anyway. So let's look at some immediate consequences of the group axioms. The first of these is the result that the identity element is unique. Now, we've kind of assumed that it was. I've kind of, in the way we've talked about it, we've referred to the identity element. But there's nothing explicit in the axioms that says there is one and only one element E which has that property. Now, it's pretty obvious when you think of addition of numbers. So 0 is the identity element for addition of numbers. And you think about it a bit, we're fairly sure that there's no other number that when you add it to every other number, it doesn't change the other number. That number has to be 0. But it's less obvious in other examples. For instance, think of multiplying together large matrices. So we know the identity matrix is an identity for that operation. But the operational matrix multiplication is not trivial. It's not that intuitive when you first meet it. I probably could have persuaded you that there was, I probably could have made you go off and look for another matrix such that when you multiply it by any other matrix, it leaves it unchanged. It might have taken you a while before you realized that that was a fruitless search, that there wasn't another identity matrix. There was only one. Well, if you've got a group, if all 4 properties are satisfied, you can very quickly show that there's one and only one identity element. And the way we do this is we suppose for a moment that there might be 2 identities floating around. We call them E and F. So E and F are 2 identity elements for the group. And then what we do is we consider the product E times F. We multiply the 2 identity elements together. And we ask what that is. Well, one way of looking at that product E times F is we remember that E is an identity element. So when you multiply E by anything else, it doesn't change the anything else. It doesn't change the other element. So E times F has to be F. But then we look at it for a second time, look at E star F for a second time, and this time we take note of the fact that F is an identity element. And that means it has the property, when you multiply anything else by F, the anything else doesn't change. The other element doesn't change. So by the same reasoning, E times F has to be E. So this element, E times F, has to be simultaneously F and E. The only way you can be simultaneously 2 things is if, in fact, those 2 things are the same thing. Okay? You can't have a mathematical object that is simultaneously equal to 2 different unequal things. So E star F, it's equal to F, it's equal to E, therefore E has to be equal to F. Okay? So any 2 identity elements, they're just different labels for the same element. Okay? So that's an initial consequence of the group axioms. In a very similar way, we can prove that inverse elements are unique. Now, if you think of it in the setting of large matrices, multiplying large matrices, the fact that the inverse matrix is unique for a given matrix, it isn't at all obvious, really. You think of multiplying together two 10 by 10 matrices. So suppose the first matrix, suppose you check its determinant and you realize it does have an inverse matrix. So there's another matrix, you multiply the two together, you get the identity matrix. Are you, how confident are you? Do you believe that could there be another inverse matrix for that original matrix? When I know in linear algebra you met a formula, you met a method for constructing the inverse matrix, but how do you know that there was only a unique inverse matrix defined? Are you really sure that there mightn't be a few different inverse matrices? When you look at it some ways, it's kind of not immediately obvious. But it does follow from the collection of those four group axioms. So let's see how the argument goes. So this time, we start with an element G, and in a similar kind of techniques as the previous argument, we start with an element G, and this time we suppose that there's two inverses for it. F is an inverse for G, and also H is. These are elements in the group. I'm not saying which group it is. It could be any group. I'm speaking now, this argument is about all groups. Okay? Anything which is a group. So G is our object element, and F and H are both inverses for G. And this argument you start, and you see this long line of equations at the end. You start in the middle. We're thinking of the triple product, F times G times H. We're studying that. Now that's a triple product, so by associativity, we know that the two ways of evaluating it pairwise give you the same answer. So to the left of the middle equal sign, we've got F times G times H. And on the right of the middle equal sign, we've got F times G times H. Now the law of associativity says that they are both the same. That's why we have the middle equal sign. But now let's move to the left. Once you've bracketed together G times H, we remember that H is an inverse for G. So G times H is equal to the identity E, and E times F has to be F, because E is the identity. So on the one hand, F times G times H is equal to F. But then you start in the middle and work right. Now you're looking at the product F times G first. You have to evaluate that first. What is F? F is introduced as an inverse to G. So F times G is again the identity element E. So you're looking at E times H, but E is the identity, so E times H has to be H. So this triple product is simultaneously equal to H and equal to F. So that tells you H and F have to be the same. Okay? So what potentially looked like two different inverses for the element G at the start, in fact, they are the same element. Okay? So the inverse element in a group is, there's one and only one inverse element for each element in the group. Some elements have this unique, this kind of quirky property that they are their own inverses, like the three reflections in the dihedral group D3 that we just looked at. They are their own inverses. Okay. And I mean, we could sit here for hours drawing out increasingly sophisticated consequences of the group axioms. Okay. There's a couple more of them there. I'll leave you to read through those. Theorem 5.3 is a cancellation law. It says when you're looking at group equations, you can cancel elements from either side. So you've got A times C equals B times C. You can cancel the C's. You conclude that A must be equal to B. You do that by multiplying both sides by the inverse of C. And Theorem 5.4, now you've already met an instance of Theorem 5.4 when you looked at multiplication of matrices. Stephen taught you about inverse matrices, and there you learned that the inverse of a product of matrices is the product of the inverse matrices, but in the opposite order. Okay? We met this You may remember it when you see the formula for matrices A and B. I mean, if we're allowed to multiply them, and if it has an inverse, the inverse of a product is the product of the inverses, but crucially, the order changes. So the inverse of B on the left and the inverse of A on the right. Okay? This is not a special particular property about matrix multiplication. It's a very fundamental property about transformations in general. We met it in the chapter on functions. The inverse of a composition of two functions is the composition of the inverses, but in the opposite order. For functions f and g, we had exactly the same property. If we're allowed to compose them, and if the inverse function exists, it follows the same pattern. The composition of the inverses, but in the opposite order. In fact, that same property holds in all groups. Okay? It's a very fundamental idea. Okay? And the proof of it is given there in 5.4. But again, this property about inverses exactly corresponds with the everyday, it's a property of reality. When you have to undo operations, you have to undo them in the reverse order to which they were applied. About how you get dressed and undressed. You take off your clothes in the opposite order to that which you put them on, if you do it in the standard way. So it's just a property of reality, really. Okay. So I want to show you some more examples of groups. Okay. So these are the modular arithmetic groups. They're on page 62. Now, some of you may have seen these before. At the face of it, at first glance, it just looks like normal operations on integers. Addition and multiplication. But it's not the normal addition and multiplication. We're doing addition and multiplication with respect to a modulus. A modulus is another non-negative integer, another positive integer n. So a plus b modulo n is equal to a number c, where c is the small remainder you get, and by small I mean between 0 and n, the small remainder you get after addition, after dividing the sum a plus b by n. And a similar definition for multiplication. So e.g., modulo 5, now what is 3 times 4? 3 times 4, well, of course, is equal to the integer 12. But the integer 12, if you divide it by 5, you get a remainder 2. So the way we write that is 12 is equivalent to 2 modulo 5. So what we say here is that the value of applying this operation 3 times 4 modulo 5 is 2. The same token, another example, what's 4 plus 4? Okay, it's the integer 8. But modulo 5, this is 3. What remainder do you get when you divide 8 by 5? 5 goes in once, remainder 3. What remainder do you get when you divide 12 by the modulus 5? 5 goes in twice, but a remainder of 2. So this 2 here is the remainder. So we can make groups out of these operations. Okay? For the additive groups, Zn plus, so the set Zn plus Zn is the set of elements 0, 1, 2, up as far as n minus 1. This is what's sometimes called a complete set of residues modulo n. These are all the remainders that you can obtain when you divide integers by n. You always get a remainder between 0 and strictly less than n. Now for multiplication, You see, not every pairs of elements have inverses under multiplication modulo some modulus. Yeah, let's consider modulo 8. If you consider products, consider the products 2 times x, where x is an element of Z8, which is the set of elements 0, 1, 2, up as far as 7. We might be searching for the inverse of 2, which is the element from this set, such that when you multiply it by 2, which is the x from this set, such that when you multiply it by 2, you get something congruent to 1 modulo 8. Well, 2 times 0 is 0, 2 times 1 is 1, obviously, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, which is 0, modulo 8. 2 times 5 is 10, which is 2, modulo 8. Everybody understand the modulo? So 2 times 5 is 10, but we're working modulo 8. So when you divide 10 by 8, you get a remainder of 2. That's the 2 there. 2 times 6 is 12, which leaves a remainder of 4. There's only one last element left to check. 2 times 7 gives you the integer 14, which is equivalent modulo 8 to 6. So where is the inverse of 2? Well, there is none. There isn't any other element. Sorry, I wrote 2 times 1 equals 1. Why didn't someone correct me? 2 times 1 is 2. So all these equations are modulo 8. So there is no inverse for 2. So this system does not have an inverse under multiplication modulo 8. This system of 8 elements, 0 through 7, under the operation of multiplication modulo 8 is not a group, because at least the element 2 does not have an inverse. And 4 or 6 won't have inverses either. 0 doesn't have an inverse. Now, that doesn't mean there isn't any group lurking here. There is a group. If I attach a superscript multiplication sign to Z8, this is the notation for a set of x such that 0, well, let's say x is in Z8, this Z8 I've written out here, and the GCD, the greatest common divisor of x and 8 is 1. So there's a condition that has to be satisfied in order to have a multiplicative inverse modulo n. The number has to be co-prime to n. So GCD equals the greatest common divisor, or you might have met it as highest common factor. HCF is less commonly used term. Greatest common divisor is the standard term. So 2 and 8 have a greatest common divisor of 2. 2 is the largest number that is a factor of 2 and 8. But 1, 3, 5, and 7, those are all co-prime to 8. This is explained in the notes, the terminology. What's the greatest common factor of 3 and 8? Well, it's 1. Okay. Greatest common factor of 5 and 8 is 1. Greatest common factor of 7 and 8 is 1. So the claim is these numbers all have, well, the claim is when you consider any modulus, so here example 8, when you consider the set of elements that are co-prime to that modulus, then this will form a group under multiplication modulo the modulus. Okay? So we could look at the Cayley table here for this group. So we're doing multiplication modulo 8. There are 4 elements involved. Now 1 is clearly the identity. You multiply a number by 1, the other number, the result is the other number. So you quickly fill it. The first row and column of the table are, even though I've made a mistake, they are easy to fill. And then you start to fill the other entries. 3 by 3, which entry goes here? 3 by 3? 1. 3 by 3, okay, it's 9. But what's 9 equivalent to modulo 8? 9 leaves remainder 1. 3 by 5 is 15. 7. 3 by 7 is 21. 5. So 16 remainder 5. Now, this group, because it's based on multiplication of integers, this group is commutative. So 5 by 3 will be the same as 3 by 5. So this will be 7 again. 5 by 5, 1. 25 divided by 8 leaves the remainder 1. 5 by 7, well, it has to be 3, because 3 hasn't appeared yet on that row. Check it, 5 by 7 is 35, which is 32 plus 3. So 3 is the remainder. There's another example of a different kind of group. And obviously this, okay, there's an infinite family of these kinds of groups. You can look at the group of integers under multiplication modulo n for any integer. Okay? So these groups feature a lot in number theory. So if you're choosing the number theory and cryptography unit next year, you'll get to know these very well. Let me just very quickly put down another group. So I've just got a couple of minutes left. So the multiplicative group modulo 5 is the multiplicative group modulo 5. So we'll very quickly put down the Cayley table. I think there's a couple of different features we can see in these groups. In the group modulo 8, every element is its own inverse. Okay? Whereas in the group Z5, you see something slightly different. By definition, any number raised to the power 0 is 1. 2 to the 1 is 1. 2 times 2 is 4. 2 cubed is 2 times 4. And you look at your Cayley table, 2 times 4 is 3. And 2 to the power 4 in this group will be 2 by 3. You look at what 2 by 3 is, you get back to 1. This group has the very nice property that it's generated by just one of its elements. Okay? Because here, this bunch of equations shows that if you start with the element 2, that's all you need. 2 to the 0, by definition, generates 1. 2 to the power 1 is itself 2. 2 squared is 4, 2 cubed is 3, 2 to the power 4, you're back to 1 again. So using powers of 2, you can generate the whole of the group. Yes, question? 2, yeah, that's the same mistake I made earlier. Okay. 2 to 1 is 2, thank you. So now it's correct. That is all of Z5. So these groups a cyclic group. It's cyclic because it has a generator. This is the definition of the term. A cyclic group, as it's generated by one of its elements. Whereas the group Z8, the integers under multiplication modulo 8, is clearly not cyclic, because if you take any of the elements, it just generates itself in 1. So it fails to generate the whole group. Cyclic groups, the structure of cyclic groups is a lot simpler than non-cyclic groups, because they're, in a sense, just generated or seeded by a single object. Okay, I've gone a couple of minutes over, but we've opened up exercises 1 and 2 there. So exercises 1 and 2 from page 69 are available to you, either for the tutorial today or for your tutorial next week. Okay, we better end it there for today. Thank you.